Today I thought we would solve a second order linear recurrence, and that's a recurrence of the form R2 a sub n plus 2 plus R1 a sub n plus 1 plus R0 a sub n equals 0. And our seeds are going to be A0 and A1. In other words, A0 and A1 are known quantities. And we're going to use a Z transform to solve this. Okay, let's get into it. So using the Z transform, we'll get R2 times the sum as n goes from 0 to infinity of an plus 2 z to the minus n, plus R1, the sum as n goes from 0 to infinity, an plus 1 z to the minus n, plus R0, the sum as n goes from 0 to infinity of an z to the minus n will equal 0. Just taking the sum as n goes from 0 to infinity on each side after multiplying both sides by z to the minus n. So for big enough z, this will be a convergent sum. Okay, well, changing our index a little bit in each term, this will yield R2 z squared times the sum as n goes from 2 to infinity of an z to the minus n, plus R1z, sum as n goes from 1 to infinity of an z to the minus n, plus R0, the sum as n goes from 0 to infinity of an z to the minus n equals 0. Just re-indexing the first and second term here. Okay, now we want all the sums to start at 0. So for instance, in this first sum, we're going to add in the n equals 0 and n equal 1 term, but then we have to subtract it. And in the second sum, we're going to add in the n equals 0 term, but then we have to subtract it. So that leaves us with R2z squared times the quantity minus A0 minus A1 over Z, plus the rest of it, the sum as n goes from 0 to infinity. Then for the second term would be a plus R1Z times the quantity minus A0 plus the sum as n goes from 0 to infinity. And then plus our third sum, we just bring that one down, that one doesn't change. Okay, bringing things together and moving it to the other side and such, we get the sum as n goes from 0 to infinity will equal R2A0 z squared plus the quantity R2A1 plus R1A0 times z divided by the quantity R2z squared plus R1z plus R0. Now, I want to let capital R1 equal minus R1 plus the square root of R1 squared minus 4R2R0 over 2R2. That's simply the first root of the denominator. And likewise, our capital R2 will equal the other root with the minus square root. Just the quadratic formula there. Okay, then rewriting the sum, we could say it's equal to z, I pulled out a z in the numerator here, times the quantity R2A0z plus R2A1 plus R1A0, all over, I pulled out the R2 in the denominator, so it's R2 times z minus R1 times z minus R2, just factoring the denominator. Now, I'm not going to go through the whole business of it, but using partial fraction decomposition, as we all learn in calculus when we do integration, this will give us this big mess. So this will equal z over R2. Well, I'm just bringing that z over R2 down. Now the rest of it, I'm using partial fraction decomposition. So that leaves us with first term minus r1 r2 a0 over 2 times the square root of r1 squared minus 4 r2 r0 plus r2 a0 over 2 plus the quantity r2 a1 plus r1 a0 all times r2. This is r2. It looks like square root of 2, but that's actually an r sub 2 there. Sorry about that. Then over our discriminant, or the square root of our discriminant. That's all over z minus r capital R1. And then our second term will be very similar. Just a couple of changes of signs. That minus will turn into a plus, and this plus will turn into a minus. And this will be all over z minus our second root, capital R2. And I'm going to define this big thing right here, just for simplifying in notation, as z over R2. Well, that's just the same as that. But then this numerator here I'm going to call capital A1. And this numerator of the second term I'm going to call capital A2. So I don't have to rewrite this whole mess over and over and over. Okay, now I'm going to do something sneaky. I'm going to take this z to the denominators. So this will equal capital A1 over R2 times the quantity 1 minus capital R1 over z plus capital A2 all over R2 times the quantity 1 minus capital R2 over z. Why do I do that? Well, this looks very much like the sum of a geometric series, these two here, and that's why we do it. Okay, well, in that regard, this thing will equal A1 over R2 times the sum as n goes from 0 to infinity of capital R1 to the n, z to the minus n, plus capital A2 over little r2 times the sum as n goes from 0 to infinity of capital R2 to the n, z to the minus n again. This will just be our common term, R1 over z, or R1 z to the minus 1. We take that to the nth power in our sums, and similarly on this sum. Well, let's bring these sums together. We can bring them together because they both start at 0. So this equals the sum as n goes from 0 to infinity of capital A1 R1 to the n over R2 plus capital A2 capital R2 to the n over R2 all times z to the minus n. All right, now let's compare this infinite sum, or infinite series, I should say, maybe, with this. This is what we started with. This was an z to the minus n, and this is this quantity z to the minus n. So by the uniqueness of power series, these coefficients must be equal to each other. So in other words, our little a sub n will equal capital A1, capital R1 to the n over R2, plus capital A2, capital R2 to the n over R2. And that will complete our video. Thank you very much.